Good evening, ladies and gentlemen. Welcome to the May meeting of the Royal Astronomical Society Victoria Centre. I'm Chris Peirce, the Centre President. Do we have any visitors here with us tonight? One. Welcome, welcome. Yes. I do have some complimentary copies of the Sky News magazine if anybody would like to pick them up down here, especially if you are visiting us. So while I have this up on the screen here, we do have a few of the commemorative beer glasses left. We're selling them for $8 each, or 2 for $15. So you can see me after the meeting, they're just down here. And they are, as you can see, they have a picture of John Stanley Plaskett with the dome on one side, and then the brewery logo on the other. Focus, yeah, there. And brewery logo on the other. Okay, so on tonight's agenda, we have our normal observing reports, if there are any, announcements, upcoming events. So there are quite a few coming up this month that we'll be talking about. We'll have our guest speaker, and then you're all invited to come up to the 4th floor lounge in the Elliott building for coffee, tea, and cookies. So if you don't know where that is, ask somebody and we'll get you in the right direction. So one of the things that we like to start off with, if there's been any observing, is if anybody wants to share what they've been doing. We've had a pretty dismal winter, but it seems like things were starting to clear, and we're getting some more opportunities to see some of the sky. There's certainly been a couple of the star parties. We've had 2 fairly decent nights, one not so good, and the only problem is with it staying light so late, is that our main target becomes the sun, and the sun has been kind of quiet lately, to say the least. But there was a little tiny sunspot visible last Saturday, and some not too bad prominences around the sun. So we did see some of those, but it wasn't a huge amount. But there were quite a few wows, and that was good to hear. So I think some people were quite impressed by what they saw. And for the people who are looking through, especially like a hydrogen alpha telescope for the first time, I think they find that quite neat. I don't know if anybody else has anything to share from the VCO or Diane.
We went to the VCO. Bruce opened up Bruce Lake, and it was really quite nice. I was going to go Monday evening, and we saw a lot of really nice messiers through the 16-inch Ritchie-Chrétien. And they were really quite spectacular. Really, so if the nights are clear, I recommend you going up. Most of the Fridays we've been going, the Saturdays, unfortunately, most of them have been cloudy nights. But if there's an opportunity to come up, do come, because the telescope is really, it's really marvelous.
Thank you, Diane. For those of you who don't know, VCO is Victoria Centre Observatory. And we purchased a newer telescope, or a new telescope, I guess, actually coming up to almost a year ago. We ordered it, but it's now installed and I think pretty much fully operational. And it's really doing a nice job. So if you want to become an active observer, you can come up and use that facility. Great. Okay, so we'll move on to the announcements phase. Last week we had a really neat event. And that was the plaque to commemorate the designation of the Dominion Astrophysical Observatory as a National Historic Site of Canada was unveiled, corresponding with the 100th anniversary of first light of the Plaskett telescope, which was officially on May the 6th. And so a number of the centre members were in attendance, and thanks to Chris Gaynor for this photograph, which I grabbed. This is the plaque that will be installed I believe in kind of in the perimeter of the parking lot close to the dome, sometime during the summer. And so it's now official. The designation happened some time ago, but the plaque had never arrived and had never been presented. So it's very good to have it here. And it was very nice. Quite a few members of the descendants of some of the early astronomers were there, including at least one person who lived on the hill as a child, which was quite neat. And there's an interesting, I think, minute and a half on Czech TV website. You may still be able to find it talking with him. Great. So, yeah, so that's, I don't know if anybody else had anything to add about that from the people. Some people were there. It was a very nice ceremony. Currently, our membership is at 277, but we do have 25 people on the grace period because we have quite a large group whose membership expired at the end of April. So we'll see. There are some familiar names there, so I think it's just people are busy with other things, so they haven't renewed their membership. And so I think that's all I have. Reg.
Hello, everyone. Before I say anything more, Tony and Sebastian are new members of the Victoria Center of RASC. Please put up your hands there so people can see you. Tony signed up her whole family for this, so that's good. So thank you, and I hope you enjoy your activities with us. And please stay after so we can make sure you get on the active observers list and find out about these things. As it was mentioned last week, there was an outbreak of Plaskett fever, and even your hardened editor of Sky News succumbed. And so the latest edition of Sky News has got an article on Plaskett and some photos, so please check it out when you've got a moment. It's online. I have a limited number of copies if anyone wants one. See me at the end. Thank you.
Great. Thank you, Rich. Anything new, Deb?
Oh, not too much. I'm still chasing the farm.
Right, okay. One of the things Deb is doing is trying to find a venue where we could have our star party this year, as we decided to abandon the winds of Machosen, but trying to find a place that wants to accommodate this rowdy group that we are, of people who stay up all night and do weird things with telescopes, is proving to be rather challenging. So. But if you do have any suggestions, you could let Deb or Bruce know. Joe isn't here this evening. Bruce?
Our current members count stands at $12,631, which is pretty much right back at where we started right when we basically said, hey, let's get a shiny new telescope. So it comes full circle financially, which is nice. So we're again at the more of Santa than Scrooge again, which is nice. So for upcoming projects, if we need to pay for rental on a star party, if Sid decides we need another solar telescope, we're in good shape for that sort of thing. Just not for my big vacation plan.
Thank you, Bruce. Ken will be back, but he had to leave because he forgot to bring something tonight. But we do have some outreach events going on. And so if you are available, I think we've got this Sandwich Strawberry Festival coming up first, and that's usually in July, and then we've got a Fort Broad Hill event in August. 10th, I think. Is it the 10th? Yeah. And then, of course, the Sandwich Fair. Plus, we're carrying on with these summer star parties at the DAO. So if anybody isn't already volunteering and would like to, you can let us know. Sid is away this week, but I think Lori was going to say a few words about the schools program.
So Sid and I are still continuing to do the school program. In fact, actually, Sid has emailed me 3 times in the past 3 or 4 days with regrets to schools that we simply can't do anymore. And I don't think we've ever had to do that. It's just been just crazy this year. So I'm wonderfully crazy. Let's not put it the right way back. It's been really a tremendous success, and we've really seen an awful lot of kids and an awful lot of teachers, and we've been to a lot of schools. So it is winding down. I believe that next week we have in the evening we have got some people coming to North Sandwich School. I don't know where you are.
On the 17th?
Okay, it's the 17th
Yeah.
is a Thursday night to that for a group of lovely behaved grade sixes. Yeah, okay. So that's kind of our last. I think there's one more after that. But we're going up tomorrow and to a graduate school, and so we've got lots still going on there.
Yes, okay, thank you, Lori. Okay, so one of the other major events this year is we're hosting in Victoria the association, the Professional Astronomers Association, and Jim Hesser is going to say a few words about where we're at there.
Well, things are going very well. The local organizing committee is getting very nervous because we have about 300 people registered for the meeting from the 22nd to the 26th of the month. The beautiful website you can blame on tonight's speaker. It's just gorgeous, and Karun has been working very hard on it for a long time. I particularly wanted to remind everybody that on Wednesday, the 23rd of May at 8 p.m., Bob McDonald is giving a free public lecture in the Conference Center Theater, which seats 400 people. There are no tickets, so the seating will be on first come, first served basis. He's speaking on what if everything we know is wrong. Quite an intriguing title. And if the theater fills up, it will be videoed onto monitors in the lobby area. I just want to remind people that the conference organizers have allocated 2 tables, one for RASC and one for the FDAO. They are in an absolutely prime location in the lobby of the conference center. And on that Wednesday evening would be a tremendous outreach opportunity to connect with community members who are attending Bob's lecture. And that afternoon, from the coffee break at 3:30 until the talk at 8 o'clock, the elementary school teacher workshop is underway. And the following day, all day, the secondary school teacher workshop is underway. So if anybody from the center or the Friends of the DAO wanted to have a presence there and try to promote or make people more aware of this absolutely amazing array of excellent activities that this group does, it's a prime opportunity. It would be really nice if there was some kind of a summary poster, at least there, so would demonstrate some of the range of activities done by the center. Both Peter Broughton, who's the author of The Northern Star, the biography of John Stanley Plaskett, he will be speaking at the conference on Wednesday morning, and then Bob McDonald is speaking that evening. Both are bringing books for sale, and they would love to have a volunteer to help with the sales of their books. So if there's anybody here who'd be willing to help out with that, I'd really appreciate it if you see me after the meeting. And although it's not strictly a Casca thing, it's the day before Casca, the Friends of the Dominion Astrophysical Observatory have organized marching or walking participation in the Victoria Day Parade, and they've sent out an email message about signing up and ordering a t-shirt. The idea is that everybody who goes in the parade will be wearing one of these very nice t-shirts. So I don't know, Laura, do you want to say anything else as the official?
I think you put that website on.
It's in Sky News.
Yeah, okay.
It's in Sky News.
So you go to the specific sign up place, and you simply just say, yep, you'd like to be in the parade. And then once we have all those people, then we will send another email out to you saying, order a t-shirt, how big, how big does it need to be? You're all going to be wearing blue, there's no difference in the colors or anything like that. And so I think that should be, quite a fun, quite a kind of a fun morning. I think it starts at 9 and goes.
Yeah, I think the get there is at 8 or something.
Something like that. Yeah.
But now we don't have a Mayfair Shopping Center parking lot. I'm just wondering how they're arranging that now.
We haven't gotten those details yet. So
that used to be the rallying point, but now it doesn't really exist anymore. So, or a large chunk of it doesn't.
Well, yeah, I don't know whether they're still going to do it
So
on the.
be on the roof of the parkade.
So, yeah, so please come. It should be kind of a fun day where they have the big banners and kind of just walk along the street. And I've never been in the parade. I certainly watched it lots, but I've never actually walked in it. So, and now that Gary has brought back my walking sticks from Arizona, I'll be fine.
Great, thank you. National Representative Nelson, do you?
Nothing new to report other than that the DA is June 28th through July 2nd in Calgary, and they'd love to have all of us sign up in the tent.
Yeah. So how many people here are going to Calgary? A few. And where is the General Assembly next year?
Toronto.
Toronto, right.
And it will be around June 20th. It's not on
A bit earlier. Yeah.
It'll be a joint meeting with the American Association of Variable Star Observers. So,
right. That'll be different.
Yes.
Yeah. And that's the again for new members and people who maybe don't know, that's the annual general meeting of the National Society, which we hosted here in 2014. Quite a neat event. Maybe while I've got you speaking, Nelson, we're in the process of revising the bylaws of the center, which are required by legislation, and Nelson's heading that effort up. So I don't know if there's anything where we are at the moment other than you're doing some revisions, and we hope to have that out maybe as early as prior to the June meeting. Is that?
Yes, it's we have what we call a final draft that we're working on. There's 6 or 8 people that are actively involved in proofreading it, and it's extraordinary how many times you can look at this thing and overlook misspelled words. It's just mind-boggling. So, but we're working on it, and the end is in sight. I guess that we'll have a complete final copy of it.
So our steps after this will be to distribute it on the Sky News list to all members for input, and we will likely call a vote for early in the fall, because it has to be approved by a special meeting. Are there any questions about that? Great. Tech Committee, Matt.
We did some collimation work on the new telescope just recently. Very minor adjustments to both the focuser and the secondary mirror. Aside from that, everything was pretty much in order. Working through a couple of bugs, supplying power to the new focusing controller. Eager to get that going as soon as possible, and that'll be the next major milestone.
Great. There.
May I ask a question of that?
Sure.
How long before we get remote access?
What's your risk threshold?
Well, I'm just thinking of being able to have classes or some other people.
And then we have a person on site controlling and streaming content to anyone who can receive it, kind of in the same fashion that we do with this right here for the meeting broadcast. We definitely accomplish that anytime. We just need a little bit of coordination on having this tech here as well as an MC to help them.
This is a representation from the designer of the t-shirt that's been referenced for the parade, by the way. So it's quite a nice looking t-shirt. And that's the back, sorry, it's my email client, but that's where the pictures are.
Can we get it as a golf shirt?
No, not this time around. But,
We're trying to keep the price
yeah.
really down.
Doesn't take any strokes off your dream, but it has
Okay, here's a list of some upcoming events. One of the things that's on at the moment at the Royal BC Museum is they have in the free gallery, I might add, a display about the first 100 years of the DAO. So I haven't been there personally, but I understand some people have, and it's very nice. And I understand that once that run is over, it will be relocated to the Center of the Universe building on the hill. Is that?
Yes,
fine?
going
Yeah.
up into the lobby.
So according to the Royal BC Museum, there's a couple of days next week it won't be on. So that's what that excluding means. So
That's the launch of their big.
So they're
Egypt, that's the Egypt,
right.
yes,
So,
okay, right.
And as been mentioned, the Victoria Centre Observatory is meeting on Friday evenings, of course, when weather permits, so the active observers get invited to do that. We're participating in the summer star parties at the DAO on Saturdays, and that will continue till September the 1st. Astro Cafe is entering its last few meetings until it takes its summer vacation, but there's 3 more, I guess, in May. And as has been mentioned, the Victoria Day Parade, the information is in the Sky News magazine. The idea is to walk in the parade to promote the 100th anniversary of the telescope. And one of the suggestions from the designer, and I don't know if that's going to happen, is that the t-shirts would be in 4 colors, but they'd be kind of spacey. Is that not doing that now?
No, I think it could be that we may be able to do something fancier for after, but the actual t-shirts for the parade is going to be just this one color at this point.
Yeah.
But we'll be making t-shirts that will be able to be sold.
Yeah.
And for the 100th anniversary. So.
That's great. Okay, and the final thing is there's, being that it's summer, there's going to be renovations taking place on campus. And one of the areas that is going out of service is the Elliott Building Lecture Theatre wing, which is often our backup space. So anything that was planned for there is now being moved somewhere else. So in June, this room is not available to us. So we have booked the Engineering and Computer Science Building, room 124. The Engineering and Computer Science Building is the one that's outlined there in that kind of purplish color. So if you park, do you have a laser? If you park in the regular parking lot that you may use, which would be this one, and we're in that A wing right there, instead of coming up to the front door, if you walk along this pathway, there's a row of buildings on both sides of you. It's in the last building on the left. So sorry about that, but we're a lower priority than university business, so we're not here next time. And of course, then we'll be having our summer recess of meetings, so then the next meeting will be in September after the June meeting. Did I miss anything, or anybody have any other announcements? Lori?
I have just one more. The Friends of the DAO, as we talked, are having the Saturday Star Parties, and they are free. Tell your friends. Have people come up and get the tickets. They're on eventbrite.com. But on June the 9th, which is just about a month from now, we are having our one and only night that will be a fundraising night, and we are going to be asking people to have if they want to come to have tickets. Children are free, but the adults are going to be $25. This is instead of having we used to have an auction, a silent auction and a live auction, and we want to get more families and more people involved in it rather than having an auction. So that's what we're doing on June the 9th. It will start at 5 o'clock. We're having there's going to be food and a DJ, and we've got all kinds of children's programming coming up. We have J.D. Matthews coming from Vancouver, who's going to be our main speaker. And we are going to be open through till 1 o'clock in the morning. So we've been given an extra couple of hours because, of course, it's so light out. We can't do any real observing. So we're going to be doing some work with the telescope. So that's going to be a long night. Any volunteers, of course, that would like to come up and help us, you come up free. That's not a problem. However, I happen to have some raffle tickets here for a raffle that we're having of a telescope and an astronomy basket, and they are as Sid said from other years. They are 1 for 5 and 3 for 10, and if anybody, I just happen to have some raffle tickets here. If anybody would like to buy a raffle ticket, that would be great. So I would hope to see you on June the 9th. Yes, Bruce.
Has there been any work done as far as making sure with the link up with commissioners about letting us come up a little later for the telescope so we don't accidentally get subcams or anything like that?
Oh yeah, yes. There will be access up so that people can come up at a little bit later time to put the telescopes up.
We could just dump our telescopes down at the DCO or the 1.22 meter, like basically up there, just above there for parking for telescopes. You just dump our stuff on, set up.
That's right. Yeah. So we'll be. In fact, actually, the actual people, like the real people, the visitors are actually going to be shuttled from the Commonwealth. Because there's so limited parking now on the hill, but we didn't have enough space. So the volunteers are actually getting the parking that night, okay. and the people who are going to be shuttled by buses back and forth from the Commonwealth. Okay.
Great, thank you. Anything else? Rich.
Our speaker this evening, Karun, recently discovered a black hole. It's called the Local Organizing Committee of Castle, and it's going into the vortex here. And it's a major achievement that he could pry himself away from this entity and deliver a talk for us tonight. We're very fortunate. Karun acquired a degree in mechanical engineering in southern India. And then he went to Concordia University in Montreal to study robotics, and then pursued a PhD in astrophysics at UVic, and he obtained a PhD in 2009. He then went and worked as a research officer in the Canadian-French Hawaiian telescope in Hawaii, and he found out that a lot of the work with that telescope involves robotics, so he was able to employ his expertise to keep all sorts of systems there running. But he's got a really keen interest in gravitational lensing, and that's what he's specialized on. But you can often see him around campus because he's a senior astronomy lab instructor, and in the wintertime he's usually wearing a black tube that says Darth Matter on it, and the little word coins. So.
But this year they'll say Big Dipper.
Thanks for the plug.
Thank you, Ron.
Can you hear me? Is the mic working? Thank you so much for that first of all, the kind invitation and the introduction as well. So it's a real pleasure for me always to share what really fires me up, the science, the research with the general public, and especially with astronomers like you. It gives me a chance to reflect on what I'm doing, why I'm doing it, and to also see this kind of a shared thought that you may have, the direction that you could suggest that I could take my research in. So it's a real pleasure to be here this evening and share something that is really enriching, that has enriched my life in the recent past. So as we all know, the universe is filled with awe-inspiring phenomena, and human curiosity aims to unravel and understand the physics behind this, aided by the laws of physics as we know it, and also with the help from technology. So as an observational cosmologist, what I focus on is trying to understand how the universe started off in this Big Bang as a very hot, extremely dense, what we call a primordial soup, slowly expanded, cooled down, and then evolved into this incredible complexity that we see around us, as shown in this image. So some of the questions that I wish to understand is focus more on the very early galaxies, the so-called dinosaur galaxies. Trying to understand, did they have structure like the Milky Way has? What kind of stars were being born in those galaxies? How many stars were formed per year, for instance? These are the questions that kind of keep me up at night, so to speak. It's not that serious. They keep me up during the day when I scratch my head and try to ponder on these questions, trying to understand these kind of fundamental questions. So gravitational lensing falls in that category. It's one of those phenomena. And thanks to Einstein's general theory of relativity, we have a fairly good understanding of the physics behind it. And also, thanks to technology, astronomers have innovated many different ways by which they can use gravitational lensing to use it like nature's telescope, to look back into the universe as a tool. So in today's talk, that's going to be the focus of my talk this evening, to kind of explain in general terms how gravitational lensing works, and also how astronomers are using it these days as an observing tool. So first of all, what is gravitational lensing? So to kind of illustrate that principle, what I have here is an eye-band image of a patch of sky taken with the Hubble Space Telescope. So this image is thanks to a team led by Andrew Fruchter at the Space Telescope. So what we're seeing here is an eye-band image taken with many hours using the Hubble Space Telescope, and it goes down to a surface brightness of 27 magnitudes per arcsecond. So to give you a point of reference, that's 5 magnitudes fainter than the night sky. So just a blank sky, it's 5 magnitudes, and 5 magnitudes in astronomers speak is 100 times fainter than the darkest sky seen from Earth. Okay, so that's the brightness of these objects. And it's taken Hubble many hours of stacked imaging to get an image like this. But this is the kind of image that I, as a cosmologist, need in order to understand the very early universe, because given the distances, the objects at these early times are extremely faint. So even with the biggest telescope, you need hours and hours of iteration time to get any signal at all. So these are definitely projects that need the biggest and the best of telescopes these days. So definitely not something that you could do with the telescopes that we have here. So in order to kind of explain things much better and improve the contrast, what I'm showing here is the same patch of sky, but this time taken in 3 different filters corresponding to the red, the green, and the blue. We make a color composite in what is called the RGB color image. So it's a true color image. And added to it, the astronomy team also did spectroscopy on many of these objects shown in this patch of sky. So what they found is, in this region, most of these blobs, these yellowish bright blobs, are, there are thousands of them, and all of them are at about the same distance, what we cosmologists call a redshift. And I think, because I've been using this term redshift quite often, you may have heard of the redshift in other presentations, I'm sure. I thought I'd just kind of remind you of what it means. So the redshift is a unit of measurement. It's a 2-for-1 unit of measurement, because cosmologists use it to measure time and distance. It's similar to a light year. For people who work in the nearby universe, you talk in terms of light years. But because the distances involved in cosmology are much greater, the unit is another unit called redshift. So, to kind of explain it, we know that the only messenger we have in astronomy is light. And the one constant about light is its speed. So as far as we understand light, the speed of light is a constant anywhere in the universe and for all time, one of the basic tenets of our physics. So what this means is, if by some magic we can figure out when the time of travel of a light signal from a source to us, then we can infer the distance to that source. Or if you flip it around, if by some way we can measure the distance to a source, we can infer how far back in time that signal was emitted. So, other than just this kind of a back and forth between distance and time, it also helps us write measurements much more simply. So to give you an example, the galaxies I showed you in the picture are all at a redshift of 0.18. And in terms of time, if I were to convert it into units of time, that corresponds to 2.8 gigalight years. Okay? That's about 3 billion years. And so we are seeing these galaxies as they were 3 billion years in the past. If I were to convert it into distance, that's 3 followed by 22 zeros, that many number of kilometers. Okay? So that's the distance between us and these galaxies. And both these bits of information is encoded in this little unit, the redshift z equals 0.18. So I can figure out not only the time of emission of the signals, but also the distance to these galaxies. So that's the big advantage of using redshifts in cosmology. So going back to what we were looking at, the image, so there are, in fact, nearly 10,000 galaxies, all at the same distance, bound together by the gravitational pull of dark matter, this unseen dark matter, to form almost like stars in a galaxy. These are galaxies within a bigger entity. We call it a galaxy cluster. So this galaxy cluster goes by the name Abel 2218, and it has a mass of 400 trillion times the mass of the sun. Okay, so that's the mass of this galaxy cluster. So other than that, what I would like to draw your attention to is not the galaxies here, but these other faint arc-like structures. So if you do spectroscopy on these objects, you find that they are at even higher redshifts or even greater distances, sometimes as high as redshift 2. And these turn out to be galaxies in the background. So the cluster is more like a foreground object, and these are galaxies way in the background. And for some reason, we are able to see them. So normally at these redshifts, we will not be able to see these galaxies at all. But as you can see, they're very clearly visible. So something is boosting or brightening these galaxies, and that's what we call a gravitational answer. And in this presentation, I try to kind of give the physics behind how this boost happens, how this magnification happens. So just to give you a picture to hold in your mind, this is like a 3D rendering of what this phenomenon is. So in this image, here we are on Earth, the observers today, we're looking out into space, and at some high redshift there is a galaxy, which is emitting light in all directions. So normally, the light beams would be like these white lines here, just going off, diverging in all directions, getting fainter with distance. But some of the light rays which pass close to this cluster of galaxies, shown here by these orange lines, for some reason, this reason of gravitational bending, they get curved or bent by the pull of gravity, and they come to a focus almost like in a telescope. So these bundles of light, which come very close to the galaxy clusters, are getting deflected very much like in a glass lens, and they're coming to a focus just because we happen to be at the right spot. So that's one thing you have to keep in mind. You have to be lucky if you actually get this gravitational lensing. You have to be at the right spot. There is no focusing involved in these gravitational telescopes. So as we look out, so as you can imagine, in this image I've just drawn two of these orange lines, but there will be many more of these light beams, all of them converging on Earth. So if each light beam carries a certain amount of brightness, we put together a bundle of 100 of them, then the brightness of this background galaxy is boosted up 100-fold. So that's the gravitational magnification or the boost. So what would be, say, just one light beam is now 100 light beams. So we're able to see things which are extremely faint, magnified much, or boosted up in brightness much better. That's why we're able to even see these high redshift galaxies. So that's what makes a gravitational lens. So now that we know what a gravitational lens is, just a little roadmap for what are the topics I aim to cover. So I'll just kind of explain how this bending of light that we saw in the previous slide happens. Okay, I'll try to keep it totally non-math, just graphics, using pictures. I will be touching upon Einstein's theory because that forms the basis for this whole phenomenon. Then we'll get into a little bit of a history. I'll kind of explain how it was first theorized and then observationally verified. Then get into the different types of gravitational lenses, what we call the gravitational lensing group, and move on to some of the applications that astronomers are putting these gravitational lenses to, and finally end with some concluding remarks. So, what causes gravitational lensing? Okay, so in order to understand gravitational lensing, we need to understand gravity. And in gravity, there are two schools. There were two schools, there is only one at the moment. So back in the 1600s, Newton explained gravity, but then nearly 300 years later, Einstein came and turned it completely on its head. So, and it was thanks to Einstein's theory of gravity that we understand gravitational lensing. So just to kind of illustrate the differences between these two schools of thought, let me first tell you how Newton looked at gravity. To Newton, gravity was just an attractive pull, some kind of a mysterious real force that happens between any two objects with mass. So if you have two massive objects, they kind of pull each other by this force, which Newton described using this Newton's law of gravity. Now, in Newton's gravity, imagine these are two objects sitting on a flat table. So these massive objects do not affect space. Space is totally impervious. It doesn't know that there is any gravity around. The two of them are completely decoupled in Newton's view of the world. So gravity happens and space is unaffected or remains flat in Newton's picture. And so because space is flat, as we learned in high school, if we have a light beams travel in straight lines, so the straight lines will just continue on for infinity. So there is no bending. So light just propagates in parallel paths as we were all taught in high school. So light rays travel in straight lines and space is flat. It is completely unaffected by the presence of mass. So that's one thing I'd like to emphasize. So mass, space, and time are completely independent of each other in Newton's view of the world. But even though I don't want to say that the Newton's theory is wrong, because it was extremely successful. It explained many of the physical phenomena that we observed back in the 1700s very well. So it works very well up to a certain limit. But the big change happened when Einstein came along and gave it much thought. And in Einstein's view of the world, there is no such thing as a gravitational force. So he called it a fictitious force. And in Einstein's view, mass and space are intimately connected with each other. So mass, if you have a massive object, the space around it curves or bends. So that's the picture Einstein put forth. And as you can see, he called it not just space, but he coupled space and time together. So in Einstein's point of view, space and time are coupled together, and space-time is intimately connected with the presence of mass. So unlike Newton, he unified these physical quantities. And so gravity in this picture is that because of the curvature, objects kind of roll towards each other. So there is no attractive force, it's purely a dynamic motion. Because of the curvature of space-time, objects fall towards each other. And that's what we call gravity. And that's the way Einstein described it, very elegantly using mathematics. So not only that, so if space is curved, and if there's a light beam traveling in this curved space-time, then naturally that light beam has to follow the curvature. Because light travels in space, space is curved, so the light beam also has to follow the curvature, as shown in this orange line here. So light rays, instead of traveling in just parallel paths, now bend wherever there is a curvature in the space due to the presence of mass. So that's the way Einstein explained this bending of light in curved space-time. So, yeah, and in Einstein's view, as you can see, mass, space-time, they're all intimately connected with each other, and there's an interaction between them. And that is fundamental to Einstein's theory of general relativity. So how does it affect us as astronomers? Okay, so here we are, sitting at telescopes, looking out into the space. So there's a distant object, and between us and the star, for instance, there's another massive object. So the space-time around that massive object is curved. So these two blue lines are two light rays. So normally, if there were no mass here, the light rays would have just carried on in the merry way. They would have traveled in straight lines. But because the space-time around this massive object is curved, the light beams kind of bend around that and come to a focus at our telescope. So this curved space-time, the curvature of space-time, is the one which is focusing, within focusing these diverging light beams. Very much like a lens, like an ordinary glass lens, the same thing, but here it's the curvature of the space itself which is causing the light beams to focus. So, a famous astronomer, John Wheeler, put it that matter in Einstein's world tells space-time how to bend, how to curve. And the curvature of space-time tells objects how to move. That was the rolling that I was talking about. Okay? So there is that interconnection or interplay between these two entities. So based on all this, of course, as I mentioned, Einstein gave us enough mathematical tools to actually compute things. So if you take an object like the sun, we can calculate by how much these light beams would bend. And it turns out to be that the bending would be about 2 arcseconds. So very much something that we can measure directly at a telescope. 2 arcseconds is quite a big amount in astronomy. So we should be able to measure this kind of deflection quite easily. Not easily, but it's not too much of a stretch. Very, very accessible even to a moderate sized telescope. And I've actually given you the formula here. As you can see, it's very compact and elegant as per all the equations that Einstein came up with. There's a sense of elegance in Einstein's mathematics, which is really beautiful. They may be impossible to solve, but they're very, very elegant to look at. So, just to kind of give you some historical notes. So Einstein first came up with this theory of special relativity, that is not using any gravity at all, in 1905. It took him 10 years of thought to come up with a general relativity. So the theory of general relativity was matured by about 1915. But back in 1912, Einstein, in discussions with an amateur astronomer, Mann, had this thought that light should actually bend in curved spacetime. But it took him a few years to actually come up with the mathematics to actually describe it. So, and it was in 1936 that he published the full set of equations to kind of compute by how much light would be deflected, using the full mechanism of GR. But well prior to that, just about 4 years after GR, the general relativity was published, another famous astronomer, Sir Eddington, said that if the sun actually should bend light, then we should be, as we calculated, it should be about 2 arcseconds. So even with the telescopes they had back then, it's a quantity that they should be able to observe. But the problem is, you can never point a telescope at the sun. It's just too bright. So what these smart astronomers did was, they waited for a total eclipse. So in 1919, there was a total eclipse of the sun. And they mounted 2 expeditions, one going to Brazil and the other one to West Africa. They used, I think, about meter-sized telescopes, looked at the sun during totality, and by a coincidence, hiatus was directly in the line of sight. So they observed hiatus during total eclipse. And if you stare intently, you can see the markings of the stars in hiatus. So they imaged the hiatus cluster, stars and hiatus cluster during the total eclipse of the sun. And what you should remember is the light rays coming from these stars, because they're passing close to the sun, should have felt that 2 arcsecond deflection. So their position should be off by 2 arcseconds. So they waited about 6 months later till the sun was clearly out of hiatus, went back and re-observed hiatus, and compared the positions of hiatus without the gravitational lensing with what they measured during the total eclipse, and they were exactly or very close to the 2 arcseconds predicted by Einstein's theory. So almost overnight, it was these observations that made Einstein's name almost a household name across the world, because this was the first conclusive proof that Einstein's general relativity was actually correct. Because Newton, being a genius, had actually calculated what would be the deflection of a light ray in his description of gravity, and that's off by a factor of 2. Or in other words, the deflection by Newton's gravity is only 1 arcsecond, whereas the GR is 2 arcseconds, and the measurements were closer to the 2 arcseconds. So this was the first conclusive proof that Einstein's description of gravity was correct. It was better than the description that Newton had proposed. Since then, there have been many measurements of the same phenomenon. So looking at the deflection of light, and as you can see, so starting in 1920, the error bars were huge back then. But as technology caught up here, so I'm just looking at the top graph. So for the time being, please disregard the lower one. So this is the deflection of light experiment. As you can see, the error bars are these big red lines. And as time progressed, we're now in the 2000s. The error bars are so tiny, we can't even see them on the clock. But still, it holds out perfectly. So the predictions of GR as far as the deflection of light are perfectly correct. So we haven't broken we haven't actually seen any variation from the predictions of GR. And this lower experiment also is kind of another way of showing that GR actually works. light delay. So to give you some history behind this, so Einstein, as I mentioned, published a full set of equations regarding gravitational lensing in 1936. And at about the same time, an unsung hero in astronomy, at least in my view, Fritz Zwicky, an astronomer at Caltech, actually said that with stars, like the sun, the deflection is very tiny, it's only 2 arcseconds, so we won't be able to see any big boost. But if we were to go and observe around clusters of galaxies, like the one that I started the presentation with, the deflection would be so high that we should actually see the magnification boost. So we should see background objects brighten, not just deflected in position, but actually brighten. So that was his prediction, but the telescopes back in 1936 didn't have the capacity to actually discover these gravitation lenses. So it took about 40 years, and the first gravitational lenses, the real boosted images, were discovered in 1979, as shown in this image here. So both these bright spots, they are high redshift quasars. The quasars are like black holes which are accreting matter, so they brighten up because they emit a lot of radiation. So this quasar at a very high redshift, so the quasar redshift is at 1.4, is being lensed by this galaxy in the foreground. Okay, so the galaxy is only at a redshift of 0.36. The quasar is at a much higher redshift, and we can clearly see that there are 2 images of the same quasar. So this was the first kind of a conclusive proof that not only do light rays get deflected, but there's actually a boost in the brightness of these background objects. And since then, of course, astronomers, once it was proved, went out and started looking for gravitational lenses, and within no time, they discovered all kinds of gravitational lenses. So the top one is called an Einstein cross. So in this case, this is the foreground galaxy which is causing the gravitational lensing. And these 4 bright spots, they're all images of a background quasar again. So this black hole again. So because of the positioning of the lens and the background source, you end up with 4 images. In the previous one, we had 2 images. In this case, there are 4 images. And so they call it an Einstein cross. In this case, what is called an Einstein ring, the foreground galaxy, the lens itself, the one which is causing the boosting, and the background source are exactly along the same line of sight. In that case, the image of the background galaxy forms a perfect ring, what is called an Einstein ring, around the foreground galaxy. So just based on the relative positions of the lens and the background source, you get different kinds of images. So those are the different types of gravitational lenses. So I started my PhD. So this was one of the projects that I undertook was, now that we know that gravitational lenses exist, let's go and find out as many of them as we can. Because using these, I can study the very distant universe. So the first thing was to discover these gravitational lenses. So we used a very wide survey done by the Canada-France Wide Telescope, called the CFHT-LS, where they imaged in 3 different filters a patch of sky 192 square degrees. So a very large patch of sky was imaged to quite a deep depth in 3 different filters. So I developed a kind of an automated search method, which went through all the stacked images looking for these gravitational lenses. So once I discovered, likely candidates, we did a visual search, so we kind of made sure that it was sensible. And back then in 2010, when this was published in the paper, we had 14 candidates, and 13 of them were new for the first-time discovery, which was confirmed, of course, using spectroscopy. So it's not enough just to confirm these using imaging. We had to go back and actually figure out that they were true lenses. So 13 of them were confirmed, and we published them in a paper. So you may wonder, so how do you, now that you know what gravitational lenses are, you can participate. You cannot observe it, we don't have a telescope. However, but thanks to big surveys, public surveys in this project called the Galaxy Zoo. So this is a survey that is ongoing at the Apache Pond by the Sloan Group. And there is so much data that no astronomer can ever use all the data. So what the team has done is they've made the data public. So they have set up a website. So you just Google Galaxy Zoo, you go to this website where every image that's being taken by the telescope is made in a form that you can access. So there's a tutorial on how to access these images. And not only that, they walk you through the steps involved in looking for gravitational lenses. So they have other projects as well. For instance, typing the kinds of galaxies. But one of the projects is to actually look for gravitational lenses in all this imaging. So if you're interested, I would invite you to go and check out this website. It's really interesting. And a lot of school children are involved in this project. It's something that even children can pick up and actually use to learn about astronomy. So how are astronomers actually using these gravitational lenses? So I just kind of illustrate 3 different applications. The first is, as I mentioned, these are nature's telescopes. So they're actually boosting and brightening things which would otherwise be impossible to observe even with the biggest telescopes we have today. So this is back to April 2218, the galaxy cluster that I introduced at the top. So in this galaxy cluster, they discovered a faint galaxy which is almost invisible in this image. That's a galaxy at a redshift of 7. So this is a galaxy that existed just when the universe was only 800 million years. So today, the universe is 13.8 billion years. So I'm talking about a very, very young universe. And even by then, it had formed its first galaxy. And this galaxy, at this distance, as I mentioned, would be impossible, even with tons of time on Hubble. It's just so faint that without gravitational lensing, we just wouldn't have seen these galaxies at all. And so that's why we call it nature's telescope, because it helps us explore a universe that's completely beyond our access, at least the current technology. I'm sure in the future, we'll be able to look at these objects, but at the current time, these are galaxies that would be impossible even for the biggest telescope. So not only does gravitational lensing help us discover these objects, but also teaches us a lot about both the foreground object, which is causing the bending of light, because it is the mass of that object which is causing the bending. So if I can measure by how much the light is getting bent, I can figure out how much mass there is in this dark matter cluster, because I have no other way of measuring mass. So this gives me a way of estimating how much matter there is, dark matter there is in this nearby cluster. I can also understand the physics going on in this background galaxies, because I'm getting the light from this very distant galaxy, so I can actually figure out its chemistry, its star formation rate. So not only can I understand about the foreground cluster, but I can also understand about this very high-energy galaxy. So it's a 2-for-1 deal. It's a real bonanza. So how do we do it? So just to give you a simple kind of a flow chart on how all this happens. So what we do is we assume, we don't know what the mass distribution is. So this is the foreground cluster which is causing the bending. We don't know how much mass there is to begin with. I have no way of knowing that. So I just assume, looking at all the galaxies, I make an assumption of how much mass there is. And also, I have no way of knowing what the true shape of the background galaxy is, or how bright it is. So again, I make an assumption about the galaxy source, its light distribution. Then I build a mathematical model, what we call a gravitational lens model. So I build a mathematical model. I run light rays through that model to generate images. So what are the kinds of images that should appear if all my assumptions are correct? And I compare what I generate with the mathematical model with what I actually observe at the telescope. So I have something to compare it with. So I generate thick images, compare it with the real images, and if I got everything right, then it's done, home free. Okay? My mathematical model is correct, so I've actually modeled the galaxy and the galaxy cluster. But as you can imagine, it takes the duration of a PhD before I get that right. So most of the time, it's this endless loop of trying to tweak the parameters in my mathematical model till I get it just right. And even though I make it sound very difficult, given the techniques we have, numerical techniques we have, there are many ways by which we can tune these models to give us the right answers. So we do have many galaxy lenses, gravitational lenses, which have been very well mapped, which have been very well modeled. And using one such model, here's a galaxy at a redshift of, at a redshift of 1.5. Okay, so that's the image of the galaxy. So they used a special instrument on the Gemini 8-meter telescope. They did a special kind of a spectroscopy called integral field spectroscopy. And using that, they were able to figure out just how fast this galaxy is rotating. In other words, they were able to measure the rotation speed of a galaxy at a redshift of 1.5. This is something we can only do with galaxies in the near universe. So, something that is impossible without gravitational lensing. And that's one thing I'd like to emphasize again is it doesn't just come as a point of light, it actually gives a structure. The image has enough structure that we can figure out just how fast the galaxy is rotating. So another thing that astronomers do is, as I mentioned, sometimes these high redshift quasars form multiple images. So remember, these are images of the same object. And quasars are intrinsically time varying. Okay? So the brightness of the quasar is constantly changing with time. And because we have 4 images, and these are images of the same light source, they all should vary in lockstep. But they don't. And that's because the light rays coming through each of these images travel through a different light path. Okay? So they have traveled greater or lesser distances depending on how they came to us. So the light distance for each of these images is different, as shown in this bottom panel here. So each of them is the light or the brightness of one of these images. And so they are telling us something about the structure of space-time along these lines of sight. And one way we can understand about the structure of space-time is by using a parameter called the Hubble's constant. So, and this is a fundamental constant that describes the universe. By using this technique, we can figure out what the value of the Hubble's constant is. So this is one way we can map the geometry of the universe. The gravitational lensing not only teaches us about galaxies and their structure, but it also gives us a way of estimating the geometry of space-time itself. So I hope I've kind of given you an overview of what happens in gravitational lensing, and so I'd like to conclude. So Einstein, first postulated it more than 100 years ago, but it was only in 79 that the first gravitational lens was discovered. But then from being just a curiosity, as I've kind of shown you, it's become part and parcel of a cosmologist's toolbox. So we use it over and over. And cosmologists are very innovative and they come up with new ways by which we can harness this incredible gift from nature. And I'm sure that with further advances in telescope technology and instrumentation, this is not the end of the line. So there are many more applications that come up with using gravitational lensing. And as I mentioned, there are many ways that you can get involved in these as well. So there are public surveys which are inviting you as citizen scientists to get involved. So do check out those. And hopefully you will find ways of getting involved with the research using gravitational lensing. So thank you so much for this opportunity.
Thank you very much, Karun. I imagine there's one or two questions in the audience. Does anyone have any thoughts? Mark?
Yeah, so assuming these are in cosmological scale, time sensitive, or they only happen when things line up correctly. How long do you expect many of these to last? Like, are these hundreds of years, thousands of years, tens of thousands of years? Like, how long will we go to study?
Yeah, that's a good question. So how long will the lens, the foreground lens and the background source stay in alignment? So we are talking in terms of cosmological time, and these will last at least for the duration of the solar system. So the change is so small compared to the overall distance that they will stay aligned. We will not see any change in the shape of the lens images, for instance, by the movement of the foreground object in the background source. Having said that, I talk only in terms of the cosmological gravitation lenses. But we do have nearby gravitation lenses. We call them micro lenses. And this happens when there are two stars, and stars move much faster than galaxies at a great redshift. So sometimes the stars line up and the foreground star boosts the brightness of the background star. And we call it a micro lens because the star boost is very tiny. And this is one way by which astronomers have found planets around other stars. Because when you have this gravitational boost, not only is the brightness of the star enhanced, but also the brightness of the planet. The planet acts as a gravitational lens as well. So we can find out the presence of planets using this microlensing. And those things are very, very fleeting. It happens just as they line up, and then it's gone, and they will never repeat because the stars are moving much faster. So what they do is they image a big patch of sky. It's an ongoing experiment in Chile called the OGLE experiment, OGLE. And they basically look at a big patch of sky with tens of thousands of stars looking for these microlensing signatures. And to date, they have a handful of detections. So in that case, the gravitational lensing is extremely fleeting. It happens once and then it's gone. But it has been observed. And we do have detections of these gravitational lenses. So in that case, where it happens in the nearby universe, it's a one-time event, but at cosmological distances, it's forever almost. As far as our history goes, on the time scale of the universe, things will change, but on the time scale, on human time scales, it will not change.
Very. You say that clusters of galaxies form a lens. I would think that a cluster of galaxy has kind of lumpy matter, but you still get an image out of it. Have you figured out what kind of mass you need or what shape of mass you need to get an image?
Yeah, that's another very good question. And I kind of glossed over that, when I went through this mathematical model. I said we assume a mass distribution. The mass distribution doesn't assume a spherically symmetric mass distribution, but they also put in all this lumpiness. Because we can observe where each of these galaxies are, and the presence of a galaxy is like a peak, a density peak, an enhancement in the mass. So they don't just assume a spherical mass distribution, but they also put substructure into that mathematical model. And when they pass the light beams through this, they take all this into account as well.
And even if it's not smooth, you still get an image.
Oh yes, yeah. It's like, if you make a poorly made glass lens, you can still see the image. It's very badly distorted, but you still get an image. It's the same thing here. The images are extremely distorted. So to actually tease out the true structure, it takes more mathematics. So the galaxy image is not perfectly in focus at all. It's very, very tattered and ratty. And so we take a lot of mathematical tools to actually figure out what the shape of the background galaxy is. So a simple analogy would be a poorly made glass lens. That's what these gravitational lenses are. Nature was not a very good glass maker or a lens maker. Okay.
On the image where you had the galaxy at, I think it was Z = 7,
Yes.
was that arc detected by program or by somebody staring at that picture?
Yeah, very fair question. You know, did we put a bunch of grad students to just look at that image and figure out every object? So what they used in this image was they developed the mass distribution of this foreground cluster. As I mentioned, they built the mathematical model to a point where they could start predicting where there should be other images. And then they actually did not see the image at all. So the astronomer who came up with the mathematical model said the highest likelihood of getting a boost is at this point. So they went to Keck and they stared at that blank piece of sky for hours and hours, and right enough, there was this galaxy at a redshift of 10. So it was predicted and then discovered, and not the other way around. So they did not actually look, they did not find a faint blob of light and then they go looking for it. They actually predicted where there should be a blob of light, and right enough there was one at this very high redshift. And that's the technique they're actually using now in using the Hubble Space Telescope. In fact, this discovery initiated a survey where they took some of the most massive galaxy clusters we know, and they put Hubble on it for, I think, 30 hours on each of those clusters. And they made the data public to the astronomy community. And there was a competition to build the mathematical models and go looking for these high redshift galaxies. Because, like I said, that's the only tool we have right now of discovering these extremely high redshift galaxies. And this came as a huge surprise, because till then astronomers thought that the universe was slow in creating structure. They thought it would have taken about 2 or 3 billion years for the first galaxies to form, and here was a galaxy within the first 800 million years. So it kind of got the astronomy community very excited to see how incredibly rich even this very young universe was. And that's why this push to push it even further. If there was a galaxy at 800 million years, perhaps there were galaxies even earlier than that. So when did the first stars form? That's a question we still haven't answered. So there's a big drive to push things back.
Thank you. Lori?
You had a picture fairly early that showed the cross.
Einstein cross.
And then underneath you showed the one that was the arc.
Yes.
I think you said that the one that was the arc, you could actually tell where the star or the galaxy that it was trying to see, that it was in a certain place.
Yes.
You didn't say that about the one with the cross. So
Yeah.
is it the same? Is it the same? It's still kind of just right in behind, or
Let me bring up
the cross
the
different?
Yeah. This one here. Yeah. So in this case, the foreground galaxy and the background source are slightly offset from each other. And that's why you get this point like in, I should take that back. Even in this case, you could have a perfect alignment. Why you don't have a full ring is that the background object is a perfect point source. You know, it's like a black hole, just a dot of light. In this case, in the case of this Einstein ring, the background object is a galaxy. So it has more structure, it's more extended, and that's why you have this unbroken ring. Whereas with the case of the quasar, you just have those 4 dots, because the source is a dot of light. So that's what the difference could be. And most of the time, the alignment here is slightly offset, but in this case, it's a perfect alignment. You know, and in some cases, this is not a perfect circle. We also have seen where the ring is perfectly circular about the foreground.
How big a redshift are we going to need before Big Bang is valid?
Okay, the Big Bang is very valid. You know, none of this is actually kind of questioning the Big Bang, because the Big Bang happened. You know, I told you that the earliest galaxy we've seen is about 800 million years after the Big Bang. We can never go back to the Big Bang. it's impossible, physically impossible, because the densities that we're talking about is so high that light cannot propagate. So it's like trying to see through a thick fog. So the light beam just gets deflected by these particles so that we can never go back to the beginning. It's impossible. So what we're trying to do, what we can see is only up to what is called the CMB, where the light kind of decoupled from this P-soup, so that's the part to which we can reach. In order to go past that, we actually are building gravitational telescopes, like LIGO. That can go a little bit past that. But light itself stops at the CMB, because prior to that, it was all coupled with matter.
I guess my question kind of was, how quickly can the galaxies form after the Big Bang?
That's the question we're trying to understand. As I mentioned, this galaxy at 800 million years came as a big surprise. So till then, we did not estimate the universe would have had time to form structure, so much structure. To make a galaxy takes a lot of structure. So there was no indication that the universe would have done that, because we had not been able to look at those records. So this came as a big surprise, and we do not know if that was the first galaxy. And there is no reason why it should be. And there could be galaxies even earlier than that. So it's still an open question. It's very much a search that is ongoing, trying to find these earliest galaxies and the earliest stars. Because their structure, their chemistry, everything was different. So we're looking at ancient dinosaurs. So these are the true living dinosaurs that you're looking at. So who knows, where this search will start. I have no idea. I have no answer to that. So,
Gary?
Please keep that question. We will find out.
Yes. Why does the Einstein cross have 4 dots and not 5 or 6 or 7?
Excellent question. In fact, there are 5 dots there, and the 5th dot is actually in the galaxy. And mathematically, that's the way we can work out using the description or the geometry or the optics of space-time. We can figure out how many images there should be for any given distribution of the foreground lens and the background source. And in most of the cases, we have odd number of images. And in this case, we have 4 images which are forming across, and then there is a 5th image which falls close to the center of the galaxy and so is lost in the light of the galaxy. In fact, there are 5 images, and that's the way, because of the curvature of space-time, we can figure out how these images will form. Very much like to do basic optics, so depending on where you have a glass lens and the source, the number of images, whether you get a real image or a virtual image, we use basic optics to figure that out. So the same way we can describe all this using mathematical equations.
But do you get sometimes 7 or sometimes?
Yeah.
Or you?
So sometimes it's only 3. So as in this case, we just have 2. There will be a little dot in the middle, and then we have the ring. So it's like an infinite number of images which make up the ring. And then I think the first quasar that was discovered, this has 3. So we have 1, 2, and there'll be a 3rd one close to the middle. So like that, there are different configurations. It all depends on the relative positions of the 2 objects, and we as observers as well, along our line of sight. And we can work it out. The mathematics behind it is well understood and figure out how many images there should be. And that's what goes into my mathematical model when I'm trying to understand the background.
Okay, well, I have one question. The Canadian-French Hawaii telescope that did the 192 square degree survey, how long was the exposure in each part that they did? How long did that take to do?
It was a long survey. I think it was 4 years or 5 years in total. So it was many years that they did observations. I do not remember the details about how long each exposure was. But of course, everything was stacked together. So we went back and repeatedly plastered the same pattern over, this 4 year period.
So this is not something you do with an amateur scope.
Yeah.
But I have something to add. During the great eclipse that we've had last year, they did detect bending of light around the sun. And for that, they used a Teleview 127 millimeter telescope for that. So
Yeah.
I just thought I'd mention that for some reason.
And mind you, as I mentioned, back in 1919, they didn't have any televiews back then, but still they were able to calculate the positions of hiatus, the stars in the hiatus cluster, and get, figured out that the answer was more consistent using GR, Einstein's theory, than using Newton's theory.
Okay, well, if there's no more questions here, thanks so much. Oh, have you got one?
When a light photon that comes near a gravity well, it tends to bend inward a bit, and when it's going in, now, does it bend more when it's coming out, or bend halfway back, or what?
So it's not actually a bending of the photon itself.
No, but
But
the
it's a
design.
bending, it's a bending of the space. So light is literally traveling in straight line. So a way of picturing it is, if I take a flat sheet like this, and if I draw lines, I can draw a straight line. If I draw two lines, those are parallel lines. They will never meet. But imagine that this is the surface of a balloon. If I start at one pole, and if I draw parallel lines, as I proceed, the lines will come together. Because of the bending, the curved nature of the surface on which I'm drawing, it's not as though the straight lines are bending, it's the surface on which I'm drawing that is bending. The same thing happens to the light photons as well. Photons travel in straight lines, but straight lines in this curved space-time are bent. They're curved. So what the photon does is it just literally rolls along this curved space-time. So depending on how much curvature there is in the space, decides on how much the bending happens. So the photon is just unaffected. It's the space-time, or the space, which is affected by gravity.
So you trace that line as it goes near a heavy object, tends to bend, like your drawing shows.
Yeah.
But when it's bending, it's going down the gravity well for a while, and then it seems to have to come back out to get it when it gets away from it. I'm just wondering how that affects the bending.
Yeah. So there are two phenomena that are intermingled here. The first one, like I said, if you just assume that we're talking about the geometry of the light wave, that can be described by gravitational lensing. So that is the bending, as we call it. The second one, where you talked about going down the gravitational potential and then coming back out, there's something called gravitational redshift. So when you put a photon close to a massive object, the photon is kind of pulled towards that, because it accelerates in gravity, it gets something called a redshift. Its frequency goes up. And then as it leaves the potential well, it has to climb back, kind of pull away from the pull of gravity. And in that case, I'm sorry, it's the other way around. So as it falls in, it gets a blue shift, it speeds up, goes higher in frequency, and as it moves away from the object, it slows down or gets gravitationally redshifted. So these photons that pass close to galaxy clusters are feeding the curvature of space-time and also this gravitational redshift. So they have a combination of both factors, but the gravitational redshifting kind of balances out because there is a certain amount of speed up that happens as it falls in, and then a slowing is, that happens as it leaves. So we don't see very much of that. What we see is only the geometrical bending of the light beam, which causes the gravitational lens. So I hope, is that?
Don't have to go home and think about it again.
Yeah.
Well, I think you gave us plenty to think about there, Varun. Thank you very much. That was a fascinating talk. Is there anyone else? So as a token of respect and appreciation for your great presentation and for sharing your expertise passion with us. We have a coveted T-shirt here of the Royal Astronomical Society of Canada. So thank you so much.
My pleasure. Remember, because I need to show you. So there's my.
See you do a new one.
Yes.
Well, thanks again very much. And remember that there's coffee and tea and cookies up in the fourth floor astronomy lounge. And if anybody is interested in getting a hard copy of the Sky News magazine, please come see me. Thanks very much.